Good morning and welcome to another Micrographics webinar with myself, Carl van Rooyen, application engineer here at Micrographics. Today we'll be looking at machine design with Autodesk Product Design and Manufacturing Collection. Today's webinar is basically going to look at all of the product or bulk of the products within the collection and what the various products will be used for. So let's move into the agenda. On our agenda today, we'll have a short introduction, followed by the various sections of the design process for product development. We've got our mechanical design, simulation, electrical design, manufacturing, data management, on how can we manage all of that data, and then we'll close off with a summary and Q&A. Within each of these sections, let's say mechanical design, we would be looking at the various products within the collection that can be used to achieve that design phase. So for instance, mechanical design, we'd look at Inventor and Fusion. Simulation, we can look at using Nastran. So we'll have different products from within the collection connected to each of these sections of the design process. We'll start off with an introduction. And in the introduction, I'm going to ask 4 questions that I think most companies, at least design office managers, production managers, owners of companies will be asking themselves, and that is, how can we spend more time innovating? Now, this goes to looking at what employees are doing and trying to free up time if they are doing a lot of repetitive administrative work or repetitive design work that takes up a lot of their time. They're not spending that time innovating and pulling the company forward. So how can we spend more time innovating? Then, how can we improve performance? In this case, it could be the performance of the product itself. How can we improve that? That will come with innovation. But also, how can we improve the performance of the, let's say, the design office, get more throughput, increase time to market on designs for new products, decrease the time to market, so get to market quicker with a new product, reduce the cost of prototyping, reduce the time for quoting, various ways in which performance can be improved. Then how can we win more business? I think this comes hand in hand with improving performance. If you can improve your performance, you can win more business. But how are what ways are there in which we can win more business? And then lastly, how can we streamline manufacturing? So once the machine has been designed, we then need to manufacture. Is there a way to streamline from the design to manufacture process? So throughout the presentation, we'll be answering these 4 questions. So what is the Product Design and Manufacturing Collection? It is a collection of products from Autodesk, and I've got a few highlighted here on this slide. There are more included in the collection. The collection, I'd like to call these sort of the hero products of the collection. We have Autodesk Inventor Professional. That is your CAD application that you will be doing design work in. Autodesk Fusion as well, pretty much a sister product to Inventor. Fusion is also a CAD application, so it has its strong points, Inventor has its strong points. And I like to see these 2 products working together to achieve a final design goal. Then also we have our AutoCAD, which is your 2D/3D drafting platform. And included with the collection, you also get all of the verticals for AutoCAD, so your specialized tool sets, AutoCAD Electrical, Architecture, Plant 3D, and P&ID. So there's a lot of products just bundled in there with the AutoCAD on its own. And then at the bottom, we've got Nastran for simulation, linear and non-linear simulation, and Vault Basic for data management. These 5 are going to be the 5 that are covered within this presentation. And there are, as I said, more that do come with the software. There are a couple of Inventor add-ins like the tolerance analysis tool, Inventor nesting as well, and Inventor CAM for machining. There's also 3ds Max and Navisworks. So there are plenty of other products that are included with the collection. This presentation is going to concentrate just on the 5 shown on screen. So to start off on mechanical design, we're going to concentrate on Inventor, Fusion, and Nastran for the design and simulate portion. And these products are used to essentially create what we would call a digital prototype. You will create your design digitally on the PC inside of these products and then simulate the real world situations, loading or heat that is applied to these products. So concentrating specifically on mechanical design within Inventor, a bit of an explanation on what Inventor is for those who are tuning in and have never used Inventor. So Inventor, when it comes to general design, is a parametric modeling platform. It's a CAD product that uses parametric modeling. Essentially what parametric modeling means is that your design is history-based. You'll enter in sketches and dimensions with numbers, how long, how wide the part is, and you'll then create features like extruding to give the thickness, adding a fillet to add a radius. And all of these dimensions and features that you are adding to the design are tracked. That's the history-based portion. And you can go back and you can edit these features. You can go back into the sketch, change the length of the object. You can go back and edit the fillet, change the radius. And this will update the design according to those changes. So if we have a look at the image on the right-hand side, we've got two L-shaped sheet metal components here. If we change the length of the sketch let's say the length of that extrusion, we could change the length of that piece of sheet metal. We could also move positions of holes using the dimensions to adjust. So it is quick and easy to go back into the model and make changes and have that update with the parametric modeling. But we can't always rely on parametric modeling. So Inventor also has direct editing. This is very useful when importing data from other packages. You might be importing step files or importing from a competitor CAD product. And when you import that information, there would be no history or no features. So you can then use direct editing to push and pull on surfaces to move them around within the design. And then lastly, freeform. Freeform allows you this push and pull sort of workflow, much like direct editing, to essentially push and pull on surfaces almost like you were molding clay. And you can create nice organic shapes using the freeform environment within Inventor. So we have these 3 different design paradigms, different ways of designing, parametric, direct, and freeform, built into Inventor to assist in the design process of creating that digital prototype. Then within Inventor, we have more specialized tool sets. In this case here, I'm highlighting the sheet metal toolset. So we have sheet metal specific commands that can be used to create sheet metal components. We can then flatten them out. Now these sheet metal components, they are rule driven. You create rules to specify the thickness of the material, the bend radius that should be used by default for the material. And from there, we can use the specialized features like contour flange, various options there to add more features onto our design. Once you have that component designed out and you are happy with that product, you're able to flat pattern that or create the development. We can see that in the image at the bottom. And that there takes into account any stretching or bending, and allows you to create a flat pattern, cut that, and have it bent up for your final product. So just one of the specialized tool sets to highlight within Inventor is the sheet metal. Then moving on to assembly side, Inventor has what we call design accelerators built in. These design accelerators go on to freeing up time within the design process. The very first one, the connections, bolts, nuts, pins, etc. If we look at this design, we see that there are just within this small portion of the design, I can count 4, 8, 12, 14 bolted connections, where each connection could be made up of 4 components, a nut, a bolt, and maybe 2 washers. And so manually placing each of these down would be very time consuming. And with the design accelerators, creating bolted connections like this is a process that is somewhat automated. You would go ahead and select the 4 holes where you want to place the bolts. You select your start plane, your end plane, and you then choose the hardware that should be placed in. That process of choosing the hardware can also be saved as a template. So the next time you add in a bolted connection, you can just choose the template, saves you from having to specify the hardware every time. And so it would be quick and easy to create these connections using that design accelerator. And the same goes to say for creating framework as well. Here we have some welded steel framework for a conveyor belt. And we have what's called frame generator inside of Inventor that allows users to create reference geometry. It could be as simple as a box with a couple of sketches on it, and that represents where your frames would go. Then frame generator allows you to choose standard profiles, place those frames down on the reference geometry, and generate the final frame. You can then go in with end treatments to create things like miters or trim the frames shorter, extend the frames. You can add various end treatments onto the ends of the frames to make sure that they are aligned correctly. And this gives you flexibility. That reference geometry can be changed. You can change the length of the reference, the width. You can adjust parameters around that reference component to adjust its size. And the frame generator will then automatically update the length of the tubes or standard profile sections that were placed on that geometry. So it automates the change process. You're not manually changing each tube length individually. And then lastly, power transmission. A lot of machines need to be driven by motors and shafts and belts. And so Inventor has power transmission design accelerators built in. You can create gear drives, spur drives with spur gears with chain and belt drives. And the process here would basically be going through and speccing out your gear ratios, your chain size or belt size, and your position of your belts. And the accelerators will then, using built-in templates, generate your gears or pulleys or spur gears and place them into the assembly. So you do not have to go and manually model up each of those components. Once again, saving you time during the design process. And the same can be said for shafts as well. You can build up shafts with the various shaft elements, circlip grooves, O-ring grooves, keyways, all automated within the process. You specify position and dimensions, and it then generates those features. So those are not the only tool sets. We can also move into piping and cable and harness. So within the assemblies, we can also go into the tube and pipe environment. And this allows you to create spec-driven tube or pipe runs. The example on the right here is a mixture of solid pipe runs where we have threaded fittings and elbows. And then we also have our flexible hydraulic line, which would have had crimped fittings on the ends. And so we can pick a spec for the, let's say, the rigid piping, and we can then route the piping quite quickly and easily using the built-in sort of handle or gizmo to draw out the 3D route that we want to follow, and then have it populate according to the correct pipe lengths and the correct elbows or fittings placed where required. The same can be said for the hydraulic line. Basically, you would create a spline to connect fitting A to fitting B, and it will then insert all the correct components to create that hydraulic line. And in a very similar fashion, we can do cable and harness as well. So here's an example on the right-hand side of a printer. We can see the PC board there in the printer with a couple of connectors. And here we can basically go from pin to pin and draw in the wires that are required. We can also include the wiring loom or the harness where the wires need to be routed to avoid any moving components, and see how much space is required. This will actually go to the point of being able to specify the gauge of the wire, and it will display the correct loom size for the number of wires that are going through. So you can get a spatial requirement for the wiring in the product. And once you have your wiring harness or your loom, you're then able to create nail board drawings of that. So create a 2D drawing, lay out that harness on the drawing with bill of materials and dimensions on how to assemble the harness. So a lot of specialized tool sets. You can dig right down into the the nuts and bolts and the nitty-gritty parts of the assemblies and include as much information as required. These tool sets will give you a much more complete bill of materials, which means you can quote more accurately. And from here, we can start to look at automation. How can we automate certain tasks? Things that you might repeat over and over again. Maybe you have a design that is customizable, and whenever the customer wants changes, it might be a process that takes time. And so for these automations, we can also look at our parts and I assemblies and our logic. Now, our parts and I assemblies are essentially table-driven parts and assemblies, which would be very similar to looking up in a catalog. You would have your different rows with your different parameters or sizes. So here on the right-hand side, a very simple bolt that I pulled from Content Center, which is essentially an R part. And we have all the different columns within the table that give us our sizing for this bolt. And so once a component is set up with its different configurations in the table, all you need to do is choose the configuration and insert that into your assembly. So you choose which row you want. If I want an M4x10 bolt, I go down to row 9 and insert that row. I don't have to draw that bolt from scratch. Very similar with assemblies. In the case of assemblies, you can turn components on or off when you go down your rows. And there are other things like constraints that could be changed. But the big part here is the iLogic design automation. With iLogic, what you can do is you can create rules, very similar to Visual Basic programming. You can create rules within your design that will check things. If you set, in this case, the kettle size too large, the frame needs to be a certain width, and that can update the frame. If you choose small, the frame width and length will change and will update according to that selection. So you create these rules, you pre-configure the different options that are available to the client, and then your design is easily configurable. So as a designer, the client may come to me and say, okay, I want a 3-tier trolley with large tanks and with banjo burners. And you would go through and tick those options within the configure panel. And so you create the rules, you can then set up, this is called a form that allows you to then configure the design. And this helps automate tasks and simplify the input that is required by the designer. And then this in turn accelerates your output at the end of the day. I've got customers that have large complex machines that are driven by iLogic and Excel, and essentially they just have to create a duplicate of that machine, enter in a couple of values given to them by the client, and that machine is updated, and within a couple of hours or a day or two, they can have this really large complex machine configured for the new client quite quickly and easily. The most amount of work will go into double checking all the drawings and making sure that all the drawings updated correctly. So there they've harnessed the parametrics and the iLogic to increase their output. I'm going to jump into a quick demo here. It won't be too long. One of the few short demos that I'll be doing, well, basically the only demo I'll be doing here for this. We're going to look at the wiring and then also the iLogic. So just very basically here we have the internals of a printer, and we can see already that there are some wires displayed just as center lines, but we can update the display and we see the loom there as well. And we also have ribbon cable. And quite basically we can go into the wiring harness and we've got various options. So as part of one of these environments that we can work in, you'll see the specialized commands for it. In this case, I'm just going to do a very quick create wire. We can specify the pins to connect to. So I'm just going to do a quick jump from one connector to the next. And we can then specify things like wire ID, category, the name of the wire. So here's our color. And if we go into properties, there's some options in properties as well. Hitting OK will then insert that wire. So we can manually go pin to pin and connect all of our wires. We can also include what's called a segment. So basically a possible path for the wire to follow from one component to another. So we can see here that we have quite a long wire that needs to run along to a motor at the back here. We can place the segment in, and that segment will basically pull the wire through that segment to the motor. And just on the display point here, I'm going to go ahead and just put in rendered display, and we can actually see the wires render in, so we can see the diameter of the wire and the loom itself. Then on to the design automation, we have this trolley here, and we can see on the left hand side we have a whole lot of rules. If I go ahead and double click on one of those rules, we can get a quick look at what the code looks like. So here's a very short section. It's looking at a trigger, and then if the kettle size is set to small, then it is setting a parameter within one of the other documents. In that document, there may be rules that then take that and trigger the size change in the kettle itself. So we'll see various rules here, like make casters, that would turn the casters on and off. And so here in the form, we can go ahead and we can choose what we want. So here we have 1, 2, or 3 tier. I'm going to go with the single tier option and just hit apply to make that change. And we'll see that the frame and the drawings, we've got an option here to update the assembly drawings. Those update using the rules to automate that process. The drawing may take a little bit of time here. Takes opportunity to have a sip of coffee or water. And there we go. There the drawing is updated and we have that change. We can go back to the assembly. We can make other changes like the kettle size. I'm going to go small there, and I'm going to take the casters off and hit apply. And once again, the assembly will update according to the rules and the parameters that drive that, and the drawing as well. That was a bit of a quicker one there. So this automation allows you to quickly customize your product for the customer's requirements. Okay, heading back to the presentation, we'll now look at Fusion. A lot of what we've covered in the Inventor is also true for Fusion, except for the design accelerators. So we see from Fusion, we have a CAD/CAM option. And so from the general design side, I'm not going to re-explain all of these. We do have the parametric modeling, the direct editing, freeform, and sheet metal. So we have the same modeling options as far as the style of modeling that we want. And then in our specialized workspaces, we don't have those design accelerators like we do in Inventor, but we do have various other options within Fusion. The ones that I'm going to highlight here is the generative design and part optimization. Generative design. Actually, if we look at the image on the right here, this just leans a bit more into the parametric modeling and freeform modeling. We have a racing steering wheel here. A lot of those components would be created using parametric modeling, very specific dimensions to match the button sizes, the hardware required, the electronics that's going to fit in. Maybe the width of the steering wheel needs to be driven for different drivers. You want to update and change the width and height. But then we have freeform modeling in the handles. So those handles are very organic shaped to match the driver's hands. And so there's freeform modeling there. So this can also translate into machine design. This is just a nice little example that is available as a sample for Fusion. But from a machine design perspective, you can still do the same. Parametric modeling to set the size of the components in the machines. And if there is anything that needs to be have a freeform organic shape, that is possible as well. Now, looking at Fusion specific specialized workspaces, one of them is generative design. This is a cloud-based function. Basically allows the designer to specify areas where they need material. So in this case, the interface between the quick release and the structure for the steering wheel. So the gray sort of spider-like lattice looking component. We have this triangle at the back for the quick release for the steering wheel. And then we have these small cones where the faceplate of the steering wheel gets bolted onto the support structure. And essentially all of the almost like tree-like or root-like sections of that design are generated according to the geometry input by the designer and the input forces from the designer. So in this case here, we're saying we have existing geometry, add or generate material between that existing geometry to support the forces required. So here, what we're getting is a very strong but also very light component, and something that the designer may not have been able to think about out of their, or figure out, out of their own heads. So this is cloud-driven generative design that is built into Fusion. There are other workspaces in Fusion. We will cover one or two of them a little bit further on, but from a Fusion design point of view, those are sort of the two main things that you can consider from machine design. I suppose if I just expand a little bit on the generative design, why would you want to use this? I've got a couple of customers that weight is a big part of their machine design. They need to make sure their machines are lightweight because they may have to air freight them to customers. And so obviously the lighter the machine, the cheaper the freight cost would be. So they can use generative design to save weight. If the machine has rotating components or components that need to essentially move, be driven by motors or hydraulics, the lighter the component is, the less effort is required to move that component as well. So here you can essentially increase cycle times on machines if the components are lighter and can move quicker. And so if you're producing machines that do mass production, you can up your cycle times or up your units produced by that machine because the cycle times are quicker. Or you can keep the cycle times the same, but require less energy to actually maintain that cycle time. Now, once you have created your design, you would then need to be able to simulate real-world loadings on that design, on that machine. And so looking at simulation within the product design and manufacturing collection, we have the star of the show, Inventor Nastran. Now, this is not the only product that can simulate. We do have some basic simulation inside of Inventor, and there is also some simulation inside of Fusion. But Nastran is really the star of the show here. It is the sort of full-featured, do everything as far as simulations, mechanical simulations go within the collection. So within Nastran, we can do non-linear simulations. Now, this is just a few of the highlights. This is not everything it can do, but we can basically look at non-linear, which includes static loading or even buckling or dynamic loading. We can do fatigue analysis, thermal analysis, as well as dynamic loading. And so on the right-hand side, we just have a few examples of images of examples of the simulations that can be done. These are all basically heat and time-based or load-based simulations within Nastran. So this allows you to then apply real-world loading to the design and see how the design reacts to that loading. This reduces the need for physical prototypes, or should I say, can reduce the number of physical prototypes you go through as you test, because you can get closer to a final result digitally within your software, within that digital prototype, before doing physical, let's say, destructive testing. Then from there, from simulation, we're going to move on to a little bit of electrical design. We already covered a little bit of that within Inventor from the rooted systems point of view, creating the wiring harnesses, but we'll expand a little bit into Fusion and AutoCAD and we'll have a look at what other electrical design options we have available within the collection. So starting off with AutoCAD Electrical. AutoCAD Electrical allows you to create the schematic designs for your machinery. So if you need to include any form of electricals within your machine, you're able to generate a schematic using AutoCAD Electrical for your electrical department to follow, or for production to follow in a wiring. And these schematic designs are based on standard libraries. A couple of examples of the built-in libraries are IAC, IEEE. There's a whole host of libraries with standard symbols in. So you can do your schematic layout as well as panel layout. So you can do your physical panel layout, where all the components will go within the panel, control panel as well. And AutoCAD Electrical allows you to output reports which would show you, for example, wiring from to, where does the wire go from point A to point B, or even bill of materials of the required components. Now, AutoCAD Electrical can also tie in with Inventor. So there's a shared interoperability between Inventor and AutoCAD Electrical. So if we go back to the printer example, we had components within that printer that can be part of a shared electrical library. And so when we place those components in Inventor, we choose from the library, I want a 3-pin connector, we place it down in the design. Then in AutoCAD Electrical, you can choose that same 3-pin connector, place the block down for it, and you can wire it up in your schematic. Now, those connections are remembered, and so you can export from your schematic in AutoCAD Electrical your from to pin assignments and import that into Inventor's cable and harness environment. And that will then automatically wire up the various components because it's using that schematic to create that wiring. So you don't have to manually go from pin to pin. You can use the schematic from AutoCAD Electrical to generate the wires within Inventor. So bringing the workflows a lot closer together, once again, saving time and improving the design process and performance. Then looking at Fusion, Fusion has a built-in PCB design software as well. So within Fusion, you're able to create PCB layouts. You can do a 2D board layout, set where your components need to be on the boards, and that can then be populated as a 3D design. So here we've got a couple of circuit boards assembled for that steering wheel. So if you are doing any custom circuit boards for your machines, you are able to include that within the design process so that you can then design your housings appropriately for that. So in the case of the steering wheel here, we can consider that a HMI or human machine interface, and it's got the electronics in it, and we need to generate a housing and design a housing around that. And so in Fusion, the CAD and electronic side of things are very tightly connected, and so you can jump back and forth between the 2D circuit board layout and design and the 3D model of that circuit board. Okay, so that brings us to the end of the electrical section, and now we move on to manufacturing. So we're extending now from the design office. Okay, once we have designed the machine, then we are going to actually need to be able to make it. So we will see that it's called the product design and manufacturing collection, because within the collection we have software that allows you to output information to the manufacturing to your manufacturing floor or to whoever manufactures for you. In this case, Fusion is really the star of the show, but we do have add-ins for Inventor as well. There's Inventor nesting for nesting up of flat components, so sheet metal or boards, and so that you can then nest for laser cutting, water jet, and so on. And then Inventor CAM as well is a CAM environment built directly into Inventor for programming for CNC machining. For this presentation, we'll be looking more specifically at Fusion. Fusion is really the star of the show when it comes to make, because it also has various functions built into it for manufacturing, and it also can be expanded through extensions to include much better nesting options, much better machining options. And so having a look at Fusion within the manufacturing workspace in Fusion, we have subtractive manufacturing. So CNC programming, anywhere from 2.5 axis up to 3+2 positional machining, if you do have a 5-axis machine. If you want to do simultaneous machining, there is a manufacturing extension that then unlocks 5-axis, 4th and 5th axis simultaneous machining for Fusion as well. It also has turning for CNC lathes and cutting for laser, water, and plasma jet machines. So Fusion will allow you to open up files that were either designed in Fusion or even within Inventor, or files from other packages as well. So there's a lot of interoperability with Fusion, being able to open up designs from other packages and then program for machining. Fusion also supports various additive manufacturing processes. We see more and more customers creating complex components that need to be 3D printed through an additive process. And Fusion supports various technologies, fused filament fabrication, that would be your standard run-of-the-mill hobbyist plastic injection molding type, 3D printing type machine. Then we've got metal powder bed fusion, binder jet, SLS, and there are various more options available. So you can basically bring in your model, you can do the printing, prep, and output the code to send to the printer within Fusion. Then lastly, we've done all of this, we've been able to create our models using the various software packages, but how do we control the data? Now, Fusion controls its data within the cloud. So Fusion kind of takes care of itself with that cloud management on the data side. But if we look at Inventor and AutoCAD, that data typically would sit on a file server somewhere. Anybody could go in, copy it, move it out of there, work with it, and it may not be secure. It may not also be in a shared location that is easy to find and access. And this is where Autodesk Vault Basic comes in. As part of the collection, we have this data management package available. And essentially what Vault Basic does is it allows you to create a central storage location. It would typically be installed on a server, and everyone would have controlled access, or should I say your designers, whoever needs access, would have controlled access to that vault, and they can then basically check their files into the vault to keep it there for safe storage, and only people who have a username and password to Vault can connect and view that information. Vault has a lot of built-in functionality as well, one of them being file control. If you check a file out, no one else can check that file out and make changes. They could get it, they can download it and view it, but it would be read-only. Then you can check your file back in, and this creates a version history. Every check out and check in with a change in the part creates a new version of that part. So you can always roll back to an older version as well. These are some of the functionalities that I've listed. Others off the top of my head: renaming components in an assembly. If you've worked in Inventor and you've renamed a file that's used in an assembly, I'm pretty sure you've seen when you open the assembly, it modes and says it can't find the file. Vault allows you to rename files, but it then fixes the assembly link, so the assembly knows what the new file name is. It also allows you to move files, and it will keep that link active in the assembly. So managing file names and file locations becomes a lot easier when it's done within Vault. Vault also extracts properties, material, description, part number, and allows you to search for that within Vault. It also shows relationships between components. It shows you, when you select an assembly, what components are used in that assembly. You can select a component and see which assemblies that component is used in. And so Vault Basic gives you this data management platform that you can use to gain a better understanding of how your data is used, and it makes it easier to manage that data. So with that said, this is going to bring us to the summary, close to the end of the session. So to summarize, the product design and manufacturing collection essentially gives you options to design how you want. What I mean by this is you can design using parametric modeling. If you prefer direct editing, you can do that. If you need to create organic shapes, you can use freeform. It gives you multiple design tools, so you can choose the tool you're more comfortable with: Inventor, Fusion, AutoCAD, and more. It can allow you to automate designs through the use of our logic in Inventor to automate that design process. Once again, a lot of this is looking at Inventor as the hero product of the collection. And so we can automate the design using our logic as one of the examples. The design accelerators can be other examples as well. Then from a simulation perspective, Nastran allows you to run your simulations to make sure that you are generating less, let's say, physical prototypes for testing because you're closer to the final product digitally. Then it allows you to also manufacture through the various CAD CAM options, the Inventor CAM, Inventor plugin for machining, or Fusion. And then lastly, as we just covered now, the data management through Vault Basic. So the final thoughts with the product design and manufacturing collection: you can spend more time innovating. You can improve your performance of both the design office, but also your products. You can then win more business. And then lastly, it can also help you to streamline manufacturing. So with that, I'm going to open up to any Q&A from anyone who is tuned in live at the moment. I'll give a few minutes to see if there are any questions that come through on the live chat. It has been pretty quiet. I've kept my eye on it during the course of the presentation. I'll give you a few minutes to see if anything comes through. If not, we'll then close off the presentation. Okay, Hendrik, I see you've got a question there. How can we use parts between Fusion and Inventor? Okay, so there is a application called the, let me get this name correct here, it's called the desktop app. If I go ahead here into my tray at the bottom, I have it running here, Autodesk Desktop Connector. You will see when you log into your Autodesk account, this will be a download that is available under the products and services page. And you would sign in with your account to the desktop connector. What this does is it will link the Fusion drive to your PC. So I can browse through the Fusion, essentially the cloud drive, as if it was a folder on my PC. That then allows you to place down files from Inventor within that drive. Inventor also does have a Fusion tab which allows you to send components to Fusion. So you can send the design to Fusion, to the modeling environment. And so the desktop connector allows those files to be shared between Inventor and Fusion. Also from Inventor, you can place from that drive. So we can go into Fusion and we can browse to a specific folder in Fusion and bring in a file from that folder. I don't think I've got a file readily available to grab. Let me just have a quick look. I'm quite sure what this is, but I'm just going to grab that part. And that would then bring that into Inventor. Now, essentially, that part is brought in. It is not something that you would be able to edit inside of, let's say, Inventor. If you open a Fusion part, or if you're in Fusion and you open an Inventor part, you would not edit that part in Fusion. You would just use it there so that it's in the assembly. Okay, I see I've got a bit of an error there. If you need to make changes to that component, you would then change it in Inventor and Fusion will update to show that change. So that desktop connector is your first step to ensuring that there is that connectivity between the two softwares. Once again, if you include Inventor files in Fusion, they would be there visible in Fusion and you can design around them, but you wouldn't modify them in Fusion. You would go back to Inventor, modify them in Inventor, and then they will update in Fusion. Okay, Hendrik, hope that answers your question. That's a pleasure. Any other questions? If you are watching this video after the live broadcast, my details are now here on the Q&A screen. So call@mgfx.co.za. So if you do have any questions after the live broadcast, so if you are watching this at a later date, feel free to drop an email through to me and I can get in contact with you and answer any questions that you may have. Okay, and I think with that, what we'll do is we will close off the presentation for today. As mentioned, you can always email any questions through to me and I will then assist where possible. Thank you for your attendance. If you attended live, it's greatly appreciated. If you are watching this after the fact, that is great as well. Thank you for that. And please keep an eye out for any of our future live broadcasts from the Micrographics page. We do, or Micrographics channel. We do quite often, we do have webinars ranging from the manufacturing environment or manufacturing products to the architectural and engineering products as well. So keep an eye out for our various live broadcasts, or just go to the channel and have a look around and see if there are any tips and tricks videos there that might pique your interest. If you enjoyed this, I would ask, would like it if you would like our video, like the broadcast, and subscribe to the webpage for any more, subscribe to the channel for any more updates on live broadcasts and any videos that we post up, short tips and tricks and vlogs that may go up on the channel. Once again, thank you so much and enjoy the rest of your day or evening. Cheers.